Hello everyone, so my name is Jin-Hae Park, and again thank you for coming into my lecture on Fourier series. Okay, so today what I'm going to talk about is uniformly convergence of Fourier series and very important Gibbs phenomena. Okay, so so let me introduce a couple of definitions first. Suppose we have Fn is a sequence of functions on a set E. So we are considered E is a subset of R. Then we say that the sequence Fn converges uniformly on E. Okay, uniformly to on E. So that implies that definition, if for every epsilon there exists a natural number which depends on epsilon, such that whenever n is small n is greater than large n and x belongs to E, Fn minus f, the distance between these two values is less than epsilon. Okay, so you can understand the uniformly convergence as follows. Okay, so I don't have a space. I can use this one. Suppose you have a function. You have function. Suppose I have E. Suppose let's see. Suppose this is E, and this definition implies that. So you have a function. Suppose this is y equal fx, the function. So then look at here. The definition was for every epsilon. So for every epsilon, there exists n. So whenever given epsilon, you can consider so a sort of a band. The center is y equal f of x. So you have this is epsilon distance, this is epsilon distance. You can have something small tube like this one. Okay, so you have a tube here. I have a tube. So tube with radius epsilon. So this guy is epsilon, this distance epsilon. So whenever epsilon is given, you consider this tube. Okay, this tube. So let me make the green with the shaded areas. I have whenever you have epsilon, you have this shaded area. Then what you need to find is this. So there exists large n such that. So what does this mean? This means Fnx belongs to fx minus epsilon, fx plus epsilon. Then what you need to do is the graph of y equal f of x. Okay. Then everything sitting in here. So this guy equals y equal f nx whenever n is greater than large n. So whenever you have epsilon, you should find the natural number large n satisfying all graph of y equal f of x is sitting inside this tube. Okay, this is uniformly continuous. So uniformly convergence is different from pointwise convergence. So I think you learned this one from calculus. So if we need more, more study on uniformly convergence and pointwise convergence, you need to look up the real analysis book. Okay, so in order to consider, so now let's go back to series of functions. Suppose you have a series of functions, then whenever you have a series of functions, you need to consider partial sum Sn to be summation from n to large n fnx. Okay, this is partial sum of this series. And if we say that if Sn converge uniformly to Snx, then we say that the series Fnx converge uniformly to S. Okay, this is just definition. So whenever you have a series of functions, then you make a partial sum. The partial sum becomes a sequence. The sequence should make parentheses over here and natural number. This one converges to Sn. Then we say that the series, infinite series, converges to Sn. Okay, so that implies that the power series, the infinite series converge uniformly on E. That is the same as the sequence Sm uniformly Cauchy sequence. Okay, so you know that in real analysis, every Cauchy sequence converges, right? That's the same as Cauchy sequence, and just the convergent sequence are equivalent. That's how this is true. So these two are equivalent. Okay, so uniformly converge and Cauchy convergence, uniformly Cauchy sequence, these are equivalent. Okay, so I'm not going to prove this. This is one of the important properties in infinite series. Okay, now the question is, so when we have piecewise, whenever we have a piecewise continuous, we can compute A0, AN, BN, and then we obtained a series. So it is called the Fourier series for F. Then our question is that whether this Fourier series, the Fourier series converges uniformly to F. Okay, so this is our big question, right? This is what I'm going to explain today. So if F is piecewise continuous, then its Fourier series converges uniformly or not. Okay, then the answer is no. Okay, so in order to answer this one, we just look at very simple examples described here. So let me draw a picture. So when x minus pi to 0, the graph is this one. Minus pi over 2. When 0 pi, I have 1/2. Okay, so this is pi over 2. X equals 0, I put 0 here. This is the graph of this f of x. So this f jumps at 0, right? This function f jumps at 0. And then, but this is piecewise continuous. Okay, so this f is piecewise continuous. You can easily check. And then our f0 defined to be right-hand limit and left-hand limit of f. So this is true. So that's just observe, you just calculate. And then I just compute A0. You look at the A0, it's obviously 0. And then you compute the AN. Cosine nx is even function. This function is odd. That becomes 0. And then I compute the Bn. That's 1 over pi. Integral minus pi to pi fx sine nx. You just plug in. And you can check n equal even. This value becomes 0. N is odd. This guy is 2 over n. So finally, our Fourier series for this given function is given by this function. This is just actually Fourier series. Okay, this is the Fourier series for given this is step function. So this is the function. Let's see. So this guy is Fourier series for this guy. Okay. Now, in order to understand this Fourier series, so then we look at the Sn, the partial sum of this function, and then this function, since f is piecewise continuous, then Sn x converge to this is a pi over 2 for each x between 0 pi. So x is 0 pi, or the function f is pi, the value of the function is f of pi over 2, and the Fourier series it converges to this, because this is by Fourier theorem. So I'm going to put by Fourier theorem. So we just proved previous lecture. You can apply Fourier theorem to prove that Sn converges to pi over 2 for each 0 to pi. Okay. Also, minus pi to 0 also converges. That's in that case minus pi over 2. And also, this function Sn, the function Sn is differentiable, right? This is differentiable because this is just the sum of finite differentiable functions. So this is obviously differentiable. And when you differentiate, so you can, this is just a finite term. You can differentiate term by term. Then I got 2 times n is to 1 to in large N cosine 2n minus 1x. Okay. Then you have derivative function. You can find the maximum. Let's find the maximum value of Sn on 0 pi. Okay. Then in order to compute the maximum, because this is a differentiable function, we first get critical point. So you want to find the value x satisfying Sn prime equals 0. So, okay. So this is Sn prime equals 0. I want to solve this one to be 0. Okay. So when you look at the, and then what I'm going to do, I'm going to compute what is this value. Okay. So what I do, I multiply this one by 2 sine x. Okay. And then you multiply this one inside out. And then I got this one. And then you use the sine formula. So I just wrote down the formula here. And the sine a plus b plus sine a minus b becomes 2 times sine a cosine b. Okay. So for each term here, we have how many terms? N equals 1 to large n. You have n terms. So you apply this formula in each term and to get this guy. And then you plug n equals 1, n equals 2. So this n equals 1, small n equals 2, and then you plug small n to be large n, then it's the last term. As you see here, this term cancels out, and then you have a sine 4x term, maybe sitting here, and sitting here. So this all term gone out, cancels out. Then final or remaining term should be this term and that term. So that's sine 0 equals 0. You finally get sine 2nx. Okay. So what I hear, 2 sine Sn prime x equals this one for x between 0 pi. So, okay. So then let me rewrite. So what we have is 2 sine x summation n from 1 to large N cosine 2n minus 1 x equals to sine 2nx. And then you divide it by sine x both sides. 2 sine x both sides. Just sine x both sides. Then I got 2 sine n from 1 to n from large 1 small 1 to large n cosine 2n minus x becomes sine 2nx divided by sine x. Okay, this guy is just the Sn prime x. Okay, so Sn prime x 0 on this interval, that means sine 2nx should be 0. Sine 2nx 0. Then you can get the value for x is k pi over 2n, k from 1 to 2n minus 1. This is just using the property of sine x. Okay? So finally, what we have, Sn prime equals 0 if and only if x equals k pi over 2n when k from 1 to 2n minus 1. So we only look at the x between 0, pi. Okay? And then what we need, so you plug in, now you need to plug in, and then also, so we want to compute, second part, we want to compute the values of Sn at 2n, 1 over 2n pi. Okay? 1 over 2n pi. So what is 1 over 2n pi? So you look at the second derivative. Okay, second derivative. I can look at the second derivative, right? So then your first derivative is this one, and then you can do second derivative. So also I can use this one. So let's see. Let me rewrite here. Sn prime equals, I have sine 2nx divided by sine x. Okay, sine x. Sine x. Then using the formula, you can get this is the second derivative. So second derivative, this one squared, f this one prime, multiply sine x minus this one and this one prime. So that's exactly this one. And then you plug x, you replace x by pi divided by 2n. You evaluate this one at pi over 2n. I got this. Okay. So this is obviously negative, right? So negative. So that implies Snx has a local maximum at pi over 2n. So I don't care about the other point. All I care about this point, because this one has a local maximum. I don't care about absolute maximum on 0 pi. So I imitated only local maximum. And then you see that f prime, Sn prime, go positive when x between 0 pi, 0 over 2 pi. Okay, so this is this one, let me draw a picture. So I have here, so this is a pi, this is pi over 2n, here pi over 2n, pi 2n over 2n minus 1. We have so many points here, right? So what is the point? This point. Okay, 1 over pi, 2 pi over 2n. So I have here pi over large n. I have here. So here, some point here. This is S n pi over 2n. So between here, the function f is increasing function. This is increasing and decreasing because this is local maximum. So local maximum, that's what I have. And then I also look at f prime equals sine 2n x divided by sine x. And then we know that Sn 0 was what? 0, because Snx, where is Snx? Snx is this. You plug in x equals 0, this is a 0 term, everything 0. So what I'm doing is Snx prime, Snx minus Sn 0. So this is using fundamental theorem of calculus. This is the fundamental theorem of calculus. theorem of calculus, I got integral 0 to x Sn prime t dt. And then Sn prime t dt was this one. Okay? What is Sn? Sn prime, where is Sn prime? Yeah, Sn prime is sine 2nx divided by sine x. So this is it. Okay? And then this one is 0. Then Sn pi over 2n would be just the integral 0 to pi over 2n sine 2nt divided by sine t dt. Okay? And I want to compute this guy. And then my technique was, so this one. So you can write down this term. You can write down this term as you expand these out. T times sine 20 minus sine t. And then this will cancel out with this. So t times sine nnt will t cancels out, you exactly this one. So this term can be written in two pieces, this one and this. Okay? And then, so let me see whether we can split to integral. Okay. So first of all, what I'm going to do is this. So I just take a limit. T goes to 0. T minus sine t divided by t sine t. When t goes to 0, t is positive. Then you can apply L'Hopital's rule, because when you plug 0, then 0 divided by 0 form. And I can differentiate respect t. I got 1 minus cosine t. Denominator you differentiate with respect to t. Then I have sine t plus t cosine t. Again, when you take 0 here, everywhere becomes 0 over 0 type. Then you apply L'Hopital's rule again. Then you got sine t, denominator. Let me differentiate this with respect to t. That's cosine t. And I differentiate this one is plus cosine t minus t sine t. So that's exactly this term. Now, when you take x goes to 0, denominator becomes 1, 2, numerator becomes 1, is to 0. Okay. This is it. So when you take a limit, the right-hand limit becomes 0. And then I look at the left-hand limit at pi over 2. Then you plug pi over 2. Yeah, just a finite. Okay, this is a continuous function. Near x equals pi over 2. So that implies that this is, then also, this each term, this guy is continuous and this is continuous when t equals 0, pi. So that implies what we proved this. T minus sine t divided by t cosine t is piecewise continuous on 0, pi over 2n. Okay? So that implies, you know, we know that by sort of a Riemann-Lebesgue lemma. Okay, so this is just the same type of Riemann-Lebesgue lemma. Then limit n goes to infinity, this becomes 0. So this is just the consequence of Riemann-Lebesgue lemma. But I can prove this one. So sort of Riemann-Lebesgue lemma look like, right? So let's see. You can actually substitute. You can substitute this one by t, but I just use this one. So when your t goes to 0, this limit goes to 0. So we proved here. Then for every given epsilon, then there exists delta. Delta such that the absolute value t is less than delta, and t minus sine t divided by t sine t is less than epsilon. Okay, and then I choose huge n, large n, so that pi over 2n is less than delta. This is always true. So this one, you know, the real analysis Archimedean property. Archimedean property. So if we want to prove everything rigorously, then here you can apply Archimedean property. This is you can always find such a natural number n. And then I look at the integral 0 to pi over 2n t minus sine t divided by t sine t multiply 2 sine 2n t dt. Well, this guy absolute value is less than 1, and this value when t between 0, so here, look at here. So here, t between 0, pi over 2n. And then this should be less than delta because this is property. In that case, this guy is less than epsilon. So I have epsilon. And then the length of interval is pi over 2n. Pi over 2n. Well, this guy is pi over 2n is also less than 1/2. Okay? So this is less than 1/2. Okay. Less than 1/2. So this is pi over 2. So this is less than epsilon. Okay? That's we are done. So what we have here, for given epsilon, there is large n such that this integral is less than epsilon. So that's exactly the limit n goes to infinity, this integral becomes 0. So when you take, so here you have, the more rigorously you should have n is greater than large n, then this integral 0 pi over 2 small n, etc. absolute value is less than this, and then so if you want to put this one, then I can put more, but when you want to prove this limit goes 0, so this is actually enough. Okay, so what we have so far, the limit of this guy becomes 0. So where were we? So what we was, so we want to compute Sn pi over 2n. I have two pieces. So this integral exists. Okay. Also this integral exists. So that's the next one. So now also sine 2n divided by t, you take limit, right limit at 0, right hand limit. And then again you apply which is, yeah, just I multiply 2nt, you cancel out. And then when t goes to 0, this becomes to 1. So that would be just 2n. Okay, this exists, right? And then right-hand limit, t goes to pi over 2n. Then, well, then this guy is pi over 2n. And then this one is pi over 2n. Then this becomes 0. This obviously becomes 0. This is 2n. So that implies that this function is actually also piecewise continuous on 0, pi over 2n. So that implies this integral exists. So at the beginning, I mentioned that the function f is piecewise continuous. The integral exists. Okay. So let's go back again. So I have two integral, two terms of this term, this term. This integral exists. This integral exists. So you can write down the integral in two pieces. So Sn pi over 2n, I have split two integral. Okay, split two integral. And then we showed that when n goes to infinity, so this goes to 0 as n goes to infinity. So that's what I proved. And then when it goes to infinity, this term, so now you take n goes to infinity, this term is gone, and then you take a limit, okay, this guy. So n goes to infinity, so you got, so then make a change variable, so that's here. I have this term, you make a change variable, s equal 2n large small t, then ds becomes 1 over 2n dt. So this integral becomes exactly this one. So n is gone. So when you take n goes to infinity, you actually get this term. So this is actually finite, and this is greater than 0. Suppose that's it, sigma equals this integral. So you actually compute this guy's the numerically 1.85, etc. Okay, so this is eventually greater than 0 infinity sine t dt. So this is actually greater than this one. So what is this number? 3.13 divided by 2, 1 point. Let me. Okay, anyway, so I'm not sure this is true. So I think this may be, you can, let's see, this one was, this is not exactly, oh yeah, twice, maybe not, I'm sorry. Just forget about this part, okay. Forget about this part. Anyway, this is finite. So you know the sine graph is this. This kind, when t goes to infinity, you have this, n equals 0, this 1, 1, the function graph like this one, okay? Okay, this one. Then, so this part, okay, this is the pi, 0, okay, pi, so this is graph. So the area is actually positive. So I think this, I made a mistake here, maybe not true. So approximately this would be 1.85, but we don't care. This anyway, this is positive. Okay, then, so let me erase this one too. So I'm not sure, so let me check. Because I'm not exactly sure if this is true. Let's see. This one, negative, positive, negative, positive. Maybe true, but I don't care. So this is my sigma. Then n goes to infinity. This is always sigma. Okay, this is sigma. What it says that the what this one says that I think we need this one too. Let me go back to here. This one should be pi over 2. So I erased this. I'm sorry. I got to go back again. Yeah. I need this one. I'm sorry. I see. So this is exactly, let me draw a picture here. So this one graph. This is a pi. The graph is this 1. Like this one. So their area of this one, 0 pi sine t. And then this is a negative, this is a positive, negative, positive. And then you make a whole integral, 0 infinity here. So this area is bigger than this area. And then this one plus this negative. Okay, so then this area, this sigma is actually greater than pi over 2. So this integral, so that was correct. So then in complex analysis, you can use complex analysis. So complex analysis, you can, by using residue integral, you can actually compute this one to be pi over 2. So I got the pi over 2. This is the pi over 2. So that implies that, so S and X does not converge uniformly to pi over 2. Okay? Because the S and X, you have S and X. So this is graph pi over 2, and then it pi. So S and X, so whenever n is large, pi over 2n, the value This guy is sigma. So graph like this one. Okay. So when n is large, so this is graph of Snx. Okay. N is large, and then the graph is very small, but here still greater than sigma. Okay. Near the sigma, the converse to sigma. Then when you take epsilon to be very small, 1/3 sigma minus pi over 2, this is greater than 0. So then you can also suppose that Sn converges to, uniformly to pi over 2. Then given this epsilon, there exists a natural number such that for every x in 0 pi, n is greater than n1, Sn minus pi over 2 is less than epsilon. And then we know that the limit n goes to infinity, Sn of pi over 2n converges to sigma, you will take just n2 is a natural number. This one is less than epsilon. Now I take natural number n is a maximum of this n1 and n2. Then I take Sn pi over 2n minus pi over 2. Then by using make a subtract sigma and plus sigma, and then by using formula, so this x plus y is greater than x absolute value, y absolute value. So the same, I'm using this formula. Then this is greater than sigma minus pi over 2 minus Sn pi over 2n minus sigma. Then obviously this is less than this one. By the way, I put this one is less than 1 epsilon. This is epsilon. This is epsilon using this formula. So then I have this guy minus this. So this is exactly 2/3 sigma minus pi over 2. So what I computed here, Sn pi minus 2n minus 2 pi is always greater than epsilon. So that implies that Sn does not converge uniformly. Okay? So this is a very important example. So when you have a Fourier series of some function which have jumps. So this function f is one of a simple example which jumps at 0. So here. So this function is one of the example. This function jumps at 0. Then what happened? You have a Fourier series actually over here up down like this. And then when even n goes to infinity, so this still always has at near 0 up down. So the gap is like sigma, greater sigma. Okay, so whenever you have a jump function, and when you have a jump function, and it's a Fourier series, always have this phenomena. Okay, so that implies Fourier series in general does not converge uniformly to f. Okay, so this is one of a very simple example. So as I just write down here, as in the previous example, Fourier series of f does not converge uniformly, although it converges pointwise to f. Okay, so this example actually, the f of x is piecewise continuous. Then the Fourier series converges, but does not converge uniformly. Okay, so this happens at the point where the given point f jumps. Okay, such a phenomena is called Gibbs phenomena. So this is one of important property in differential equations. Okay, so just today I just explained when you have a Fourier series, then the Fourier series in general does not converge uniformly to given function, although it is converged pointwise. Okay, thank you very much. I will see you next time. Bye.